All right, so let's start one of the last sessions, I think, for today. I guess everybody is kind of in a hurry to rush to the bar or other more interesting activities that hear about Docker and microservices and things like that. So I will try to get to the point. And let's go. All right, so let's talk about Docker and microservices. I'm Jérôme Petazzoni. I work for Docker, so take everything I say with a grain of salt. When I say that Docker is awesome, obviously I work for them, so I can't be 100% objective, even if I try. I'm French, as you probably guessed from the accent. Nobody's perfect. I have some experience with containers and Docker and microservices. Some experience with containers because I tried to operate a large-scale platform as a service thing working on EC2, and I have some experience with microservices because this path that we were running had a lot of them microservices. When I counted them, I saw that we had like 106 microservices, so that gave me an idea of what it's like to deploy something with microservices. So the outline for today is, first I will quickly explain what exactly are microservices, then what kind of new challenge they bring, and how to address some of those challenges with Docker. Docker doesn't pretend to be like the magic silver bullet to solve everything about microservices. It will just help to solve some of those issues. So first, what are microservices? The idea of a microservice architecture is to take your big application, your big monolithic application, and break that down into many little parts. One easy example is when you have an e-commerce website, for instance, like Amazon. You break that down into a web front end, and then another service that has the catalog of product, another service that keeps track of what you have in stock, another service to compute like shipping costs and taxes, another to generate invoices, and so on, and so on, and so on. And why are we doing that? Because it lets you use a different tool, a different framework, a different language, a different database for each of those little components. If you have something that needs to be highly asynchronous, and well, then you can use Node.js or Go or something like that for it, but still stick to Python, Ruby, or Java for the rest of the stack. If there is that specific database which is great for one specific little area of the website, then that's fine, you can use that. When you go, for instance, to the Amazon website as a customer willing to buy stuff, you will see many little bits of pages that I kind of put together to show you something like that. Oh, you're looking at this product, but other people who looked at this product also looked at those other products, and other people who bought this also bought this other thing, and so on and so on. So this is a kind of the part of the tip of the iceberg of microservices. Each of those little things that you see are built by different services, so that if something goes down at some point, like, well, we just deployed a new version of the recommendation engine and it's completely broken, we can pull the plug of that thing, and basically when you load up the page, you won't see recommendation telling you that if you bought candies with Docker logos on them, then you're probably interested by remotes for presenters and things like that. So that lets you use the right tool for the right job, separate concerns, separate teams. That's great. It lets you also refactor services individually. Like if you are about to make a new version of one specific area of the website, instead of having those two branches of your code base, one with the new version using that Go thing and the other with the legacy thing in Python, you can have just that specific component in a separate repo, and you can switch from one to the other more easily, taking less risk than if you had those two branches and doing like one huge deploy of the whole code base and praying for everything to go right. It also allows to decouple deployment. Very often when you have a monolithic code base, there is that code freeze and then deploy. I remember recently talking with someone who told me, okay, so this is how we do it. We have the code base, and on Monday everything should be stable and deployable, and on Tuesday QA tries to break everything, and on Wednesday we deploy. So it's not that bad because it means one deployment a week, which by some standards is still pretty fast. However, it means that when you want to ship something, it has to be ready by Monday so that it can be tested Tuesday and deployed Wednesday. If it's not ready Monday, too late. You will have to wait one more week. If you deploy every week, it's not that bad. If you deploy every month, that starts being a problem. So with microservices, you can say, well, each individual service can be deployed whenever we want without having to coordinate on the schedule. We don't have to agree on Monday, 8 in the morning, Pacific or East Coast time. The repo has to be in a buildable, workable state, and everybody trying to rush to get their last changes in. No, each service can have its own little repo, independent from the others, and you can release at your own speed. Which means that you have the deployments, instead of being this big Wednesday event where everybody is crossing fingers so that everything goes right. Deployments become little things that you can do whenever you want at your own pace. There is less risk, so it means that you won't be afraid of deploying more often. So it means that when you are doing changes, you won't be afraid of making them, and you will go faster. That's this famous move fast and break things. It's move fast and break things because you know that it will be easier to fix things, and that you won't, for instance, have to wait one extra week to repair what you've broken. It also allows you to have an effective ownership of services. Instead of having this is the website and those are the 50 people responsible for it, you have this is the website broken down into maybe 30 microservices, and each of those microservices is owned by a small team of maybe 2, 3, 4, 5, 7 people, and each team really owns that little part of the service. They own it, which means they are responsible, which has good sides and bad sides. The bad side of that, well, if it goes down, if it breaks, if you screw up, then it's your fault and you have to fix it. However, being responsible also means that you are in charge. If you decide that the best way to implement that part of the service is to use that language, that framework, those algorithms, everything, you are free to use what you want without having to impose a decision to the rest of the whole team. If you decide that for this specific part it's better to use Java, even though everybody else in the company hates Java and does Ruby, that's fine. You can do your own little thing in Java, and everything else we just talk to your service over an API. They don't have to care if it's Java, Go, Node, Python, or anything else. So good side and bad side. On the bad side, the fact that since you are in charge, since you are empowered, you're responsible. So that means that if your service breaks, you also have the one to fix it because it's entirely your fault. So it means that developers can be put on call, which is not always a good thing, but some organizations found that it helped a lot, because when you know that your code can wake you up at 3 in the morning, that gives you a pretty strong incentive to make it work. So there is another rule, another thing, that's the 2 pizza rule. Jeff Bezos from Amazon said, never make a meeting if you can't feed everybody with 2 pizzas. So basically, depending on whether we talk about really hungry developers or people who are just out from a meal, it means maybe between 5 and 10 people. The idea here, it's not about pizzas, it's about communication overhead. If you have a big team, you spend a lot of time to synchronize and keep everybody up to date. There will be always someone who will be a little bit late and everybody will be waiting for them. And if you don't wait, then you have to keep them posted afterwards, so you waste a lot of communication time, whereas with a smaller team, you reduce the chance that someone will be unavailable. The more people in the team, then you implement high unavailability kind of on people, because you increase the chance that one of them won't be there for the meeting. All right, so now assuming that you kind of like the value proposition of microservices, what's the challenge when implementing microservices? There is this really good blog post called Microservices, Not a Free Lunch. It's interesting because that person doesn't say microservices suck. They say microservices are great, I love them, but be aware that if you go that way, you're going to face those challenges. And those challenges are the fact that you start to have a significant operations overhead. Since we have so many services all over the place, we need to have efficient service discovery. We need to have an efficient way, like if a service goes down, to bring that part back up. Instead of having just one big server and the application on it, now we have tons of servers, and part of the services are here, other services are in another machine, and so on and so on. So the plumbing, the communication between all the services becomes a problem that we didn't have before. It means that you need some substantial DevOps skills. So what does that mean? It means that before you had the code base and you had some people responsible for the deployment process. So you would have the ops team. The ops team would take the code and they would kind of force that into the servers and make it work. Now each team can do more or less whatever they want. They can use the tools, the programming languages. At Docker, we even let each team pick the infrastructure they want. So we have some stuff that runs on Amazon, some stuff that runs on Rackspace, some stuff that runs on Linode, and so on and so on. So it means that it's great because you have choice. It means that it's not so great because before you had kind of a company-wide knowledge, like this is how we deploy. We have an ops team on 10 people and they all know how we deploy. Now each of your services is managed by a team which maybe use something completely different. So the idea here is that teams should be large enough so that so that there is always at least one person available to deploy something. So even if you use a really custom weird deployment mechanism, there will be always one person who knows which button to push to make the deployment happen. But still, there are many complicated things, like how do we make backups of the database. Those complicated things before were owned by a team that had like years and years of experience and time to craft the best database backups ever because that's their job. Now each team is kind of doing their own little ops or DBA job, even if that's not their primary skill. So that can be dangerous. Implementing microservices also mean that you have implicit interfaces. So the communication between services go through APIs. So each time you start a new little service in your app, you define a new API. Actually, that could be a good or a bad thing because it means that once you have deployed a service, other people can use it, and so you should not break the API. But that's pretty much the same thing as breaking just the interface for some class, some library that you've written. So it's not a big deal. Distributed systems complexity. Okay, as it happens, when you have some code running on multiple machines, it's more complicated than when it runs on a single machine. The real big issue that bites you is the fact that network calls are more complicated than local calls. If I call a function locally, I call it, I get a return value, done, end of story. If I call something, yeah, there's a question here.
Just to comment that, like, running a microservice for us means a thick, popular front ends are client side heavy, so that just means you have lots of back end services. It doesn't necessarily relate to this. So this is only if you have a server back end that renders HTML and server side and we see it at your face.
Right. For many people, this is not a problem because instead of having to deal with one big backend API that in turn speaks to many little microservices, you have a client-heavy, like those HTML5 single app applications, as we sometimes call them, that in turns will talk to multiple APIs. And then you don't really have that problem. But yeah, the key thing is that instead of doing local function calls, sometimes you make API calls, and API calls can time out, then can fail. Sometimes the latency can spike up a little bit, and that's a new class of problem that we have to deal with. And in the same vein of idea, some things that used to be a single operation, like when someone clicks on, okay, check out my cart and pay all the things, now it's broken down into many little steps, and one of them individually can fail. And instead of just considering that as a success or fail operation, you would like that to be success or fail because that specific condition, but I was able to continue anyway. Like I was not able to send the SMS notification for your order, but that's okay. I still continued anyway with everything else because I will maybe send notification later or not at all because it's not critical. Testability challenges. So the fact that now you have many microservices, it means that instead of doing unit tests, you can be tempted to do monitoring. So instead of testing the code in isolation, you just do test API calls once in a while to check that the service is working properly. Actually, you can just have both, that's fine. It's just that it's kind of easy sometimes to say, I'm not going to write tests because anyway there will be something monitoring my service. So that being said, some of the problems described here we will address with Docker. Now, what are the things that we will not discuss? So first, how to actually decide how you will break down your application. That's software architecture. I'm not going to talk about this. How to design clean APIs, same thing. How to convince your developers to be on call and carry pagers. Apparently at Amazon, when they did that big change, they say, okay, here is a pager, either you take it or the door is that way. So that's not a very nice way to do things, but apparently it worked. We won't discuss about how to implement fast, efficient RPC calls neither. There are many things out there to do that. All right, so Docker today, how does it help with microservices? So Docker will help us with building, packaging, and shipping our code, running it consistently across different environments, because now we have, instead of having one development environment and then one production environment, I have as many environments that I have services. If I have 100 services, maybe I have 100 development and 100 production environments. So we need something to bring up those environments easily. We want to be able to bring up copies of those environments, because if your app is just Java or PHP and there is a single thing to start, you start it, done. If it's 100 services and each of them has to be configured to talk accordingly correctly to the others, just like putting up a dev stack can take hours, sometimes days, or even longer. We have people in some big banks in France who told us when using Docker, we were able to bring down the onboarding time from like almost 5 days, so 1 week of work, to like 5 minutes, and we will see how. And the last thing is that we will use Docker to abstract the network topology and service discovery. So those new problems that are not directly linked to microservices, but that become extremely important when you have microservices, Docker will help with them. All right, so first, how do we use Docker to build, package, and ship code? We use a Docker file. So I will have a quick demo of how we build stuff with Docker. For those of you who already know Docker, that will be no surprise. For the others, it will help to see what we're talking about. The idea is to write once, build and run anywhere, and then have a container image that we can deploy on any machine. Little detail, even if you're using an interpreted language like Python or Ruby, build still makes sense, but instead of compiling code, we will be downloading dependencies and installing them, so that there is still a build process. So, demo. This is how I will build a very simple container. So that's just a static web server here running Nginx and generating a little hello world page in that container. So basically I tell to Docker I want to use an Ubuntu based image, and in that image I want to apt-get update, apt-get install Nginx, generate an index.html, and that's pretty much it. And then I tell to Docker to build this. So Docker will actually execute all those operations, and at the end of each step, it will take a snapshot of my container, so that later, if I decide to change my Docker file, to change my code, to change something in the build process, Docker will be able to optimize the rebuild and reuse the steps that we have already done. So there it's instant. That's it. And now I will run this. So starting the container, and all right, I need to make a very complicated copy paste here into my browser. Right. Okay, so I just made a very simple web app with a static thing, and I put that in a container. I built that container and I've run it. Now imagine I want to change something here. Well, I will reedit this Docker file with the build recipe. Say, hi, SCaLE 13th edition, I'm in your container. I rebuild. So this time the build is almost instantaneous, because Docker was able to realize that I haven't changed the first steps of my build process, so it was able to reuse the first snapshots that it took of the container. And now I run that new version of the container. It's running on a different port, All right, and now I have the new version of my software up and running in a container. So that was pretty simple, but there are a couple of interesting things here. First, Docker files are imperative and pretty developer-friendly. If you don't know anything about Chef, Puppet, Ansible, Salt, and you have to write a recipe to deploy your software with them, the learning curve will be pretty steep. With Docker files, we hope that anybody able to write a shell script will be able to write a Docker file by just adding run in front of each line. Also, this leads to pretty reliable things. So, almost. If you can write instructions to install the code, then okay, you just put run in front of them, and that should work. And if it doesn't, at least you can test it, see if it works, and amend and test again, and that's it. And so a little detail that did not kind of jump at our face when I did the demo, but is the fact that both the old and new version of my software, so my Hello World page, are running side by side next to each other. I haven't updated my server. I actually created a new server with the new version, and I still have the old version. So if I realize suddenly, oh my God, that is something really bad, I need to go back to the previous version, I can do that very easily because I still have the old version. This is different from, oh, okay, I have updated my servers, but I need to roll back, and I don't know how. Maybe I can just check out the previous version of the code and pray that everything will work properly. So the idea here is to make some operations much easier. And once I have this container, this little Hello World thing, I can run it anywhere. So I won't demo that, but basically I can run that on my Linux laptop, on a Mac laptop over here, on a physical machine. I can run that on a virtual machine, on EC2, on DigitalOcean, on whatever. So basically the container image that we've built becomes the new build artifact, like what I ship to my ops team or to my servers if I do the deploy myself. It's not a tarball of code. It's not a jar file or a gem file or an egg or whatever you use in your favorite language or framework. It's this container image, and it's always the same, whatever you're doing, whatever you're deploying. And you can have an automated build system with that automatically builds your containers, then submits your containers to a CI/CD system like Jenkins, for instance, and if everything is fine, then it will pre-deploy that container on your production servers. Pre-deploy means the container is here, and all you have to do is press a button to switch traffic to that new version. And if anything goes wrong, you can roll back instantly as well. All right, so now how do we run multiple containers at the same time? Because the whole point is, okay, we have microservices, so hundreds of things that have to talk to each other. So each of them will be in a container, and how do we have all those containers talking to each other? We will use something called Fig for when we use a development stack. So the idea with Fig is that I have a little definition file like this one. The whole idea of Fig is to have this onboarding workflow. Ideally, in a perfect Dockerized company, when you get a new developer, the process looks like this. First, hire the developer. That's actually the most complicated part. Then give them a computer. Then install Docker with, for instance, something like boot to Docker. That's a 25 meg VM image, so that's pretty easy to set up. Then clone the code repo, run fig up, and you're done. And I'm going to prove it, which is why in my demo directory here I have nothing, it's empty, because I'm going to do exactly that. So git clone, github.com, jpetazzoni, fig demo. That's it, and now I do fig up. Right, I need to go to the repository, fig up. Oh yeah, right. So basically, you have to believe me, I really did just clone the repo, went into the directory and did fig up. That's it. And this started like a very simple web application. So it's running on port 5000. So let's see what it looks like. Right. So this is not a static web page, but a dynamic web page served by the Python Flask application, and there is a Redis backend to store the number of visits. This is so MySpace. It's worse than MySpace, I can believe that. So this is what the code looks like. So it's sorry, it's probably not very readable here, but the whole point is that it's less than one page of Python code, so super simple. And there is one thing that I want to show absolutely because it's super important for the rest of the thing. How do I connect to my Redis backend? Well, I connect to Redis. The host name, the DNS entry for my Redis thing is Redis. How does that work? So that's where Docker helps us. Oh yeah, people say that this is much better than Vagrant. I say limitations apply. Well, we had many people after testing Fig telling us that they were immensely happy about it because it was so much faster to onboard people and they didn't have to upgrade Vagrant-based box anymore and blah, blah, blah. That's all nice and everything if you're working only on Linux. If you have a more complicated stack with mixes of Windows and Linux and whatever, then Docker won't help because Docker only does Linux machines for now. Okay, I will explain the Redis naming trick in just a couple of minutes. First, I wanted to talk about test because I have another really cool demo that I want to do. So, so basically, Docker helps a lot with testing. Actually, among the first people to use Docker in production, even when it was like Docker 0.6 and we had like danger labels everywhere, don't use in production, this will empty your fridge and power out your beers and kill your dog and whatever. So, but some people were using it anyway. In those people were crazy Russians, for instance, from Yandex, the Google of Russia. We decided, well, we were about to write this anyway, so we might as well use this fancy Docker project rather than rewriting everything from scratch. And other people were people in the testing industry, because when you are running test platforms, if the test platform crashes and burns, it's okay, because it's not the code that runs for the end users, it's the code that runs when the developers are testing that everything works fine. Maybe you know Travis CI, for instance. That kind of service lets you hook your GitHub repo to Travis CI, and each time you push some code on GitHub, it will get that code and run tests, and it will show you a nice green light or red light depending on whether the test passed or not. So if you're using Docker for testing in production, that means for that red or green light. So that means that if it's broken, it doesn't mean that people going to your app see a dead page. It just means that when you push code, instead of knowing if tests pass or fail, you see nothing, which is not a huge deal. Okay, it's annoying, but it's not like business impacting, mission critical or whatever. So I have a little demo of that to explain, to kind of give you an idea of why those people in the test industry said, oh yeah, please, I want to use this immediately. And so that's the demo test. So here, when I start run test, I'm starting a container that has a PostgreSQL database, and that database has a lot of testing data, a lot of tables. So that's a Django website. So if you've done some Django, maybe you recognize those off this, off that, Django admin this, Django that. And so what I'm going to do is that I'm going to, let's see, so, right, this is going to be complicated. All right, you see in the beginning I have auth group. I'm going to nuke that. So drop table auth group cascade. Right, so now if I check again, auth group is done. Now I exit this and I start it again, and now auth group is back. So what happens here? What happens is that I have a container that has my test database, and each time I start a copy of that container, I have a brand new database, so my tests can completely wreak havoc in the middle of the database, and it's fine, because each time I get a new database. And the point of using containers here is that even if my database is huge, like terabytes of data, starting it will be fast because instead of doing a full copy, we use something called copy on write, which is, let's pretend that this is a copy of the thing, but basically each time you will try to write something to change some data, then we will keep track of what you've changed instead of changing the original. So for people doing tests, this is great because they could spin up new environments extremely quickly in a matter of seconds, and they run a bunch of tests and then throw away those environments. So Docker helps for tests. Okay, and then I will talk a little bit about how Docker helps with the networking things. This is an impossible to translate joke about the fact that there is a brand of chocolate where the tagline is the meetings of the ambassador are always a success. That's a French thing. And this is a pile of those chocolates because one of the concepts that we use are ambassadors, and this is to remind me that I'm going to talk about that, ambassadors. But first, I will talk about links between containers, so not those links, but a different kind of links. So Docker has this mechanism that I was talking about earlier where it can add local DNS entries, DNS aliases into a container. That's why in my little counter web application, in the code, I just connect to Redis and it works magically. So under the hood, when I did Fig up and started the web application, what happened is that Fig did start one Redis container, and then it started the web application container, and inside that web application container, if you ping Redis or if you try to resolve Redis, it resolves to the IP address of the other container. Another way to look at it is the little diagram where I have my Redis container, and then in my web container I connect to Redis and it resolves to the other one. If that's still confusing, I have a little example. So basically, let's do docker run --name my Redis, and I want to start the Redis image. Okay, so now I have a Redis container running on my machine. Great. Now let's do docker run. I will start just a basic Ubuntu thing, and I will link it. So my Redis, and let's say I want to call it Zelda. And so basically now if I do ping Zelda, I am just pinging the other container right next to it. So in my code, instead of doing something complicated like trying to figure out what's the IP address of the other container with magical ways, I just connect to this and it works magically. To try to prove that this is really working, so see I've left the ping running in the background here. Now I'm doing the ping from the container, so obviously that's not what I want to do. Docker attach this one. Alright, so what I will do is that while the ping is running, let me juggle a little bit with the, we can see that the thing is pinging up here. So now I'm going to connect to the same machine, and I'm going to kill that Redis container, and we will see that the ping will stop there. So docker kill my Redis, and that's it. It doesn't ping anymore. So I proved that that's really what was happening. So this means that we can run multiple stacks next to each other. I can have like a production stack, a dev stack, or maybe I'm working on developing one specific feature there and another feature elsewhere, and each copy of the code is always connecting to Redis without trying to do anything fancy, except that when this web container on the left tries to connect to Redis, it gets it to the dev Redis. When this web container on the right, the one of the production stack, tries to connect to Redis, it gets it to the production Redis. So I can keep the same code, no extra config file, no magic environment variable or whatever, and still connect to the right thing. So ambassadors are mechanisms to abstract possibly remote services. because this was nice as long as I was connecting from a local web container to a local Redis container. But what if my web container and my Redis container are on different machines? Well, then the idea is that we do something like this. So on the left, I have my Redis machine in blue, on the right, my web machine in green. I have my web container on the web machine, the Redis container on the Redis machine. So far, so good. Now we add the ambassadors. So the ambassadors, there is one of each machine. So on the web machine, I have an ambassador that pretends to be Redis. It's like, yeah, connect to me. I will behave exactly like the Redis that you know and love, and you will be able to do Redis commands, and everything will be fine. And on the left, we have another ambassador that will connect to the actual Redis and pretend to be a Redis client. And those two ambassadors will talk to each other. So basically what happens is that when the web stack is trying to connect to Redis, it connects to the local ambassador, like believing that this is really Redis, and the local ambassador then does some magic to find out where the other ambassador is running, and it will forward the traffic to this other ambassador, which in turn will pass it to the actual Redis. The nice thing is that for the web containers, this is completely transparent. There is no difference between I'm talking to a local Redis and I'm talking to a remote Redis. When I say no difference, I mean that I'm running exactly the same code, the same everything. I didn't change a single thing. Now, what do we use to have those two ambassadors talk to each other? We did extensive research on the matter and found out that the best way would be to use unicorns, precisely unicorns ridden by cats with guns and yeah, this. So what does this mean? It means that actually there is no one-size-fits-all mechanism to get those ambassadors to talk to each other. If you're deploying on EC2, then it will probably be the good idea to use something, maybe spicing it like ELB, the elastic load balancers. If you're deploying on-prem on your own physical machines in a colo with your own network, you could use VLANs and put each set of containers on those VLAN, and so on and so on. So very different mechanisms. If you want some example of ambassadors, here are some. I will share those slides so you don't have to scribble down those links right now. But basically, for different network environments, we have different kinds of ambassadors. You can also write your own, and that's what most people do those days. The idea, for instance, is that when the Redis service starts, the ambassador that is next to it will say, okay, so I will talk to a central name discovery mechanism, maybe some key value store like Zookeeper or etcd or console, and here I will write down the Redis for this stack is at this host and this port. Later, the web host comes up, and you start the container with the web application, and the ambassador that's supposed to behave like Redis, and this ambassador will look up in Zookeeper, etcd, console, and you say, okay, what's the host and port for this Redis? It will find the value that was previously put by the first ambassador, and it will know where to send the traffic. If you use VLANs instead, it's more or less the same thing, except you don't necessarily have to use a central key value discovery mechanism. You can maybe even use something like Avahi, which use multicast discovery. So basically, when this ambassador on the right starts, you say, okay, I need to connect to Redis. How do I do that? It sends an Avahi multicast packet saying, okay, who here has the Redis 5523? Well, the one I need to connect to for my buddy here. The ambassador running next to Redis receives that multicast packet and answers to say it's here on that host and port. And that's how you can do discovery. So I have a short demo with a really hacky ambassador that I wrote. It's using Hacha proxy, but I think it should stand in that case for hacky proxy. It's super simple. The idea is that we run it like this. So I'm going to connect to my other EC2 instance right here. And I'm going to start oh, we don't see anything. Great. Better. So I just do docker run -d in the background -p public Redis. All right. And Now I have Redis running on this machine on that port. Great. And now I will go to my other machine. That's the one. Okay, and I will do Docker run -d. Oops, sorry, I forgot about it. Better. Docker run -d. So I will name that my Redis, and I'm jpetazzoni /h emba. Wow, that I'm being trolled by terminal sizes. So basically, I'm starting this container. I'm calling it my Redis. I'm using my jpetazzoni /h emba image. I forgot to specify the port I want to listen to. 6379, the default Redis port. Hey, maybe if I use something slightly smaller. Right. Okay. Okay. The change of the. Yeah, I don't have an intermediate font size, unfortunately, but right. Okay, this time should be the good one. Right. So I've just started this Redis ambassador. So again, it's something that's running next to my web container, and it behaves like the Redis thing, but it's not the Redis thing. Let's get the zoom size again, and now I can. So let's see. I can go to demo ambassador, and here I will. I will start the web stack, so Docker build -webnet, okay. So I'm building it. So that's the same application with the counter. And now I'm running it, -d, so -p, 6000, that's web, and I will link it, so --link, my Redis, colon Redis. That's the line that we've been running. And now if I go to this on port 6000, normally, okay, nice demo. So what happened here? Okay, it's supposed to be running, but it's not Python, okay. Okay, in text mode it works, so maybe why doesn't it, that's the same IP address, that's the same port, the same everything, so that's weird. Let's blame network proxies or whatever, but basically if I do curl locally here, we see that I'm increasing the counter, so the IP address of the machine is not very clearly visible here, but you can see that the last digit is like 54. I'm going to go back to my Redis machine here, and I'm going to kill this Redis, again to prove that I'm really accessing Redis on a different machine. So I've killed Redis. Now I go back here, and when I do curl, it doesn't work anymore because Redis is dead. So that's how we get an application to believe that it's talking to a local service, but really it's talking to a remote service. Some people complain sometimes that we are adding extra hops and it's bad for latency, it's bad for complexity and everything. So there are a few methods to avoid the extra hops if like performance is important for you. For instance, you can set up straight DNS aliasing within a container. So you can start a container and you can tell it, okay, Redis should map to this IP address. So you can kind of dynamically inject DNS records into your container. You can also, instead of using HAProxy, you can use directly IP table rules or IPVS or even another project like Pipework to have the container join a VLAN or share a physical interface and directly connect to the network. There are many ways to do that. Sometimes those extra hops are good though. For instance, let's say that instead of being Redis, we are dealing with a SQL database like Postgres. instead of connecting to a simple redirector that just sends you somewhere, you could connect to a SQL bouncer that will take care of a few things. It can inject SQL credentials, so basically your application connects to the bouncer and without using passwords or anything like that, and the bouncer has the credentials and can connect to the actual database with those credentials. So you're separating identification and authentication from the main application. So your main application doesn't need to have database passwords anymore in it because that's still by something else. You can also use those ambassadors as API proxies. For instance, if you are using, let's say, the Twitter API and you want to keep track of how many calls you make and what's the latency like and things like that, you could put all that stuff in your main application code, of course, but you would be adding extra complexity to the application code. Instead, what you can do is you can have your application connect to an ambassador instead of the actual Twitter API, and this ambassador will just kind of update counters and take metrics of response time and whatever, and pass the data back to between the real Twitter API and your application. So again, the idea is that we decouple all the things. Your applications remains simple and efficient and not bloated with all that extra instrumentation code. There are also sometimes where extra hops are good in beer. Okay, yep.
What's sort of an example of that when you might have like MySQL connection? Or isn't your app expecting like a very specific protocol? Are you going to have to break that protocol in some way?
So what if my app is expecting a specific protocol, then my ambassador has to speak that protocol? Is that the concern? Yeah, totally. If for instance you want to connect to a PostgreSQL database and you want to be fancy about it, then the ambassador has to understand the PostgreSQL protocol. So typically you won't write your own from scratch. You will use something like a PG pool or PG bouncer, which are existing kind of they're called bouncers, but it's a little bit like a proxy, and you will set them up accordingly. So, yep.
Is Ambassador a Docker concept or just something clever you came up with?
So, Ambassador was initially the answer to how do I get containers to talk to each other if they run on different hosts. And we thought about it a lot. And at some point we say, okay, let's have those kind of proxies or something. And we call them ambassadors, for lack of a better word. To be honest, I don't know if whoever had the idea of this word picked it up from somewhere else. I should look that up someday. But I've mostly seen it in Docker and containers terminology. I'm not saying it doesn't exist elsewhere, but I've seen mostly in this context. So Docker tomorrow, and I will be very quick here because I think I'm getting things.
It's here for questions. So I want to make sure you got the mic.
Okay, well, we're almost at the question phase. So how Docker will help us tomorrow? Because everything I showed so far is stuff you can do today. You can even demo it like I did with variable results, but actually it works, it's here. So what will we have tomorrow? Tomorrow we'll have network extensions. So that's the plan B if you don't like ambassadors and you say, okay, I just want to connect directly to my other containers. So that's something to create a kind of virtual network that connects all your containers together, and each container has its own IP address. So there are multiple implementations of that concept, for instance, Weave, Socket Plane, Flannel, and then basically you can come back to the good old level 3 network that we've known and loved for decades. Then other upcoming things, Docker Machine. So Docker Machine is a tool to simplify deploying Docker, because I haven't covered that in the beginning. I came up with my Docker VMs and I did SSH and everything was nice, but how do we get those VMs in the first place? It's not hard, but still when you go from one infrastructure to the other, it's a little bit different. So Docker Machine is a project where you can basically do Docker Machine, create me one Docker VM on Azure or EC2 or Rackspace, and it will do it, and you don't have to worry about the little details. So when you want to switch to a different provider, it makes things easier. I had a demo, but we're out of time, so skip that. Then we have Docker Swarm. Docker Swarm, the idea here is, okay, now I've used Docker Machine and I have dozens of Docker VMs, that's great, but now I need to spread my containers across all those Docker hosts. So how do I do that? You can do that manually, so you can, just like I did in the demo, you log somewhere and start a container, log elsewhere, start another container. But Swarm lets you have one unique aggregated API endpoint. You still do Docker run, Docker PS, Docker stop, Docker this and Docker that, but instead of talking directly to Docker, you talk to Swarm, and Swarm will connect to all the Docker hosts that it manages, and it will schedule, it will orchestrate container deployments on them. So it means that you still have the same workflow. You don't have to learn a new concept, a new system, and you deploy containers like that. Docker Compose, that's basically like the Fig demo I did, except it integrates with Swarm and Machine to support operations like scaling, for instance. The Docker ecosystem is huge, so there are many other projects coming up all the time. So maybe you have some issue or concern that I haven't addressed here, but chances are that there is someone in the ecosystem already working on it. So recap, with Docker, we want to do repeatable, reliable builds that anybody can do without being like a sysadmin guru. We abstract the development environment so that those containers can run anywhere. Then we abstract the network so that the containers can connect to each other without having to know exactly how things are connected. We make testing easier. We make handling of compute resources, so infrastructure, easier with Docker Machine. And there is Docker Swarm, which is upcoming to orchestrate and scale out more easily. This is a bunch of links to get started. Oh, and before I forget, this image doesn't have the right size, but basically the next month we will do a kind of contribute-a-thon or something like that with Docker. We will basically try to help people to make their first open source contribution to a project like Docker. And if you're interested by that, you can go to docker.party, and in the process we will also save whales. Don't ask me exactly how, but we'll do it. If you have questions, we might have a few minutes to address them before we all...
Yeah, we certainly will have some time for questions. What I'm going to do is I'm going to interject really quickly. Our sponsorship for this room was by ActiveState, and they've got something called Stack Auto, which is based on Cloud Foundry and Docker, so it's like it's for a platform as a service. So if you guys are looking for some sort of enterprise help on this, do check them out. This is a community event. If it wasn't for the sponsors, we couldn't get you in for the kind of price we do because it helps pay for rent. So do check them out. They're also hiring, so if you've got little cards laying around like this, check them out. They're downstairs in the expo floor. Also, by the way, you just did a presentation at Mac CDN this last Tuesday for the Docker meetup in LA. So if you guys really want to learn about Docker, check out the Docker meetup in LA. And there's other Docker meetups also probably happening in other cities. So I'm sure if you're in Orange County, there might be something going on there or whatnot. So do check those out. Questions? Who's got questions? Raise your hand and I'll bring the mic to you. All right, sweet.
This is just strictly, where are the slides going to be posted?
Slides. So one of the things that he's going to do is he's going to give me the slides with a USB stick. I got a USB stick for him, and we as a conference will end up posting the slides. But I'm sure if you ping him on there, he can probably help you with that too. So we'll get the slides to you one way or the other. Any other questions? All right, sweet. I'd like to thank our great presentation here.
Oh, and this year I don't have cool Docker t-shirts because that was too much room in my suitcase, but I have Docker stickers if you don't have one yet, so I'm leaving them here.
So we got Docker stickers, and don't forget we have Birds of a Feather still going on tonight from like 7 and 8 o'clock, and the week is keep coming up later. So there's still lots of stuff to do, so if you want to just hang out and not go home yet, we got you all set. Thanks. And the party tonight, game night downstairs.